Have you ever wondered how a computer works? Or how does it do what it's supposed to do? Okay, how does it know what to do? Strictly speaking, the knowledge of the inner workings of a computer is not really required for you to understand or learn programming. But I think it's important that you at least know the basics so that you can appreciate what's happening behind the scenes when you run a program that's written in a high level programming language such as Python. It all starts with extremely tiny electronic components called transistors, which sort of act as switches. These transistors are used to make what we call logic gates. Okay? And these logic gates have a few interesting properties. For instance, if you take the AND gate, for instance, okay, so the AND gate, what it symbolized by this symbol here, okay, so it takes two inputs. So essentially, it's like running through wires through a gate, and it has one output. Okay, so if you pass both high voltage or you pass high voltage through both these wires, you'll get a high voltage in the output wire. If any of these voltages is a low voltage like so, uh, the output would be low voltage as well. Okay, so similarly, you have the OR gate, okay, in which again you have two input, right, and it's denoted by this symbol right here, and this produces a high voltage if either one of these is high. So this can be this is produce high voltage. Okay, so essentially, using a clever combination of these gates, of these logic gates, a processor, a CPU, can do arithmetic operations, or perform arithmetic operations such as addition, okay, subtraction, uh, and also logical operations such as making decisions, okay, and or. Okay, so in essence, a computer only understands voltages, nothing else, right? It only understands voltage levels, high or low. And using a clever combination of these voltages and these gates, it can perform mathematical operations and logical operations, right? Arithmetic and logic unit, addition, subtraction, even multiplication, okay, and logic operations. Also, it can copy data, right? It can send signals that copies data. Now, these voltages are essentially represented as 1, the high voltage is represented as 1, and the low voltage is represented as zeros. Okay? And this is where the binary, the word binary comes from. Okay? So you might have also heard that the computer understands binary, which means it understands two things, 0, 1. Okay? Now, in the early days of computing, okay, one of the earliest computers, which is the DEC PDP-8F, this computer actually had switches. Okay, it had 12 switches, 0 through 11, and as you can see, the switches could be in on or off positions, right? And you actually had to flip these switches on and off to program. Now, as you might have imagined, this was extremely tedious. Okay? So subsequent processors, instead of using zeros and ones, they used the hexadecimal number. Okay, the hexadecimal uh, notation, and in hexadecimal, you have 16 numbers which represent. You have 16 digits essentially from 0 through F. Okay, so you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, and F. So 16 digits, and these digits were used to represent binary. So 0 would stand for essentially 0, 1 would be 1, 2 would be 1, 0, 3 would be 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1000, 1001, okay, and oops, I messed it somewhere, but it would be ultimately 1111. Okay, so you'd use 0 through F to represent these 16 numbers. Okay, 16 binary numbers. And the way you program a Z80 microprocessor would be as follows. So the processor has a set of mnemonics, which are like instructions. Okay, so these are add with carry, add like addition, right? You'll have and, which logical and. You'll have subtraction. Okay, you'll have something like load, and using these mnemonics, you'll write a program such as this. Okay, and once you've written the program, you'd replace these instructions by their opcodes, which is in hexadecimal, like 8E and DD and FD and 88 and so on and so forth. Okay, and then use these opcodes to actually type in the code using this keypad right here. So that's how you would code a sort of a Z80 processor, okay, or one of the early processors. Again, you can imagine that how tedious this is, right? This is a program to add add two numbers, essentially. Okay, and just to add two numbers, you have to go through all of these, right? You have to first write the program using the mnemonics, and then find the appropriate opcodes, and then go back to your processor and type in the opcodes, right? To key in the opcodes, and then all that just to add two numbers. Now you can imagine this was slowing everything down, right? This is not good. So what the scientists, the computer engineers, and the good people, what they came up with was something called high level languages. Okay, high level languages. These are languages that the computer cannot understand, obviously, but it's easier for human to understand. Okay, and what happens is you have something in between, a software, another piece of software, which is called a compiler. And you would write your program in high level languages such as Python or C or C++ or Java, C Sharp, and what have you. Okay, and this high level languages would be sent to the compiler. Okay, and these high level languages would be easier for us human to understand and reason about. And this high level language would be sent to the compiler, which will then convert that language to essentially binary code, zeros and ones, right? Binary code. And that would be sent to the CPU to execute. Okay, and that's the beauty of high level programming languages. That's sort of the history of high level programming languages.